Welcome to lesson 8.3. In this video, we're going to focus on volumes of solids with known cross-sections. In geometry, you learned a number of different formulas for finding volumes of pretty common shapes, such as cubes, spheres, cones, rectangular prisms, and others. Again, these are three-dimensional shapes. In calculus, you're going to be able to find the volume of some of these solids if we know the two-dimensional region on the XY coordinate system and have a height that's formed by a cross-section that includes squares, rectangles, semicircles, or triangles. The phrase here is they essentially stick out from the base. So if we were to look at our normal XY type graph, and if we had, for example, some shape here, let's say we're going to be doing some triangles. So let's say we had something that was just kind of a wacky shape like this, that we can find the cross-sectional area in here. Okay, we can find that by using the integral. This is some f of x. When it's talking about sticking out from the base, if we were to rotate this forward so that we're now looking at it lying flat, and it was coming something like this, we know this section there, and so the sticking out from the base is this portion right here that's going into the third dimension. And so if we were looking at something that was a rectangular shape, then everywhere this would create a rectangular shape, or a square shape, or a semicircle, or whatever it is. But it would have this shape that went into it that was coming up or out of this base. And so the base shape that we're looking at is something that's defined by the XY coordinate plane, and then the Z, or the third dimension, is coming out in some type of a shape, some kind of a cross-sectional shape. So each of these here would be either a square, rectangular, triangle, whatever, semicircle, whatever it's defined as. So those are the restrictions for finding the volumes of solids in these cases. Some basic formulas for those cross-sectional areas. Square is the sides squared. The rectangle is the base times the height. The semicircle is 1/2 pi r squared. Triangle 1/2 over base times height. An equilateral triangle is a new one for me, or for many, but it has a formula that's square root of 3/4 times the side squared. This wasn't a really common one that I can remember, but you may find it on the AP test. So these are some formulas to recognize that could be used for these cross-sectional areas. So let's take a look at one of these, for example. Okay, so the cross-sectional area is perpendicular to the x-axis or perpendicular to the y-axis, and here's how it would be written. Your volume is going to be equal to this area dx, going from whatever your a to b, your two limits, where the area here is defined as the cross-section of whatever that is. So if it's a rectangle or square or semicircle, that's what's used to define the area. This is when we're looking at things with respect to our x. These are typically cross-sectional areas that go vertical. So vertical cross-sectional areas. And when we're looking at our y, we're looking at typically horizontal cross-sectional areas. Okay, so let's take a look at this first problem here. We've got an example where we've been given the volume of a solid, or we're trying to find the volume of a solid whose base is a triangle. Here's our triangle. One side here that's bounded by three equations. The first one it's telling us is this line, this y is equal to negative 2x plus 2. That's going to be this right here, so negative 2x plus 2. The second one is our x equals 0. This is this side right here. Basically, it's our y-axis. The other is our y equal to 0, which is our x-axis. Whoops. So this triangle has been formed here. We're being asked to go from 0 to 1. And this is our formula. The volume is equal to limits a to b for the area with respect to x. So if we plug this in, this is cross-sectional areas are squares. So the area for squares is our side squared. Now, when we think about this, what is it that defines our side? By the way, if we wanted to look at this, let's say we laid this down. Here's our triangle. And these cross-sectional areas that they're talking about are coming out of this. And so that's our square. We have a little bitty square here, and other squares as they go through. And so what you end up with is this this shape here, this three-dimensional shape, like this. But in each of these slices, we have this square slice that is the area that we're actually looking for. Okay, so this is going back from here in the shape of a square. So we're actually defining the side by our y value. Well, that makes it really nice and easy because we actually have an equation here. This negative 2x plus 2, that's going to be our side. So we would set this up by saying is equal to our integral from 0 to 1 of our side squared. Our side is a negative 2x plus 2, and all of this is squared dx. A couple of ways we can do this. We could go through and try and do a composition functions where we're doing a reverse chain rule. We could also square this and just treat them as a power rule. Either way is up to you. They should come out to be the same function. So I'm going to go ahead and make this into a quadratic. I'd like to see how that one goes here. So squared here, this becomes 4x squared plus, I'm sorry, not plus. In this case, it would be minus. It's the first term times the last term, which would be a minus 4x, which times 2 is going to be a minus 8x, and then plus 4 dx. So if we were to take the integral of this is going to be 4x cubed over 3 minus, this becomes 8x squared over 2, and then plus 4x. And this is going to go from 0 to 1. Nice thing about this is if we look at the 0 portion, we know all of these have got a value in, or a variable in there, so they'll all be 0, which means basically we're looking at this 1 cubed, so this becomes 4 thirds minus 8 halves, which is 4 plus 4. Well, that's kind of nice. These two end up canceling out. But if we finish this off the 0 here, this is going to end up being 0 minus 0 plus 0, which is a big fat 0, and leaves us with, if these two cancel out, this is going to be equal to 4 thirds. Hopefully that makes sense. So what we're looking at now is that the volume of this is 4 thirds. The volume of that 3D shape, this up here. All right, let's take a look at another one. This is gonna end up being the same shape. We're not going to actually integrate this. The integration part is something that hopefully you're very familiar with at this point. All we're going to do is the setup. So the first one here, we're looking at, we're going to set up, not integrate, same base as example 1. So we've got our y is equal to negative 2x squared, or 2x plus 2, sorry. Our base is our x-axis, our height is our y-axis. So we're looking to find semicircles perpendicular to the x-axis. So once again, if we were looking at our triangle here, now instead of squares, we have these semicircles. That's a terrible semicircle that are going here, and this ends up being kind of a cone shape type object. Okay, but if we think about it, this semicircle is, we've got this radius, and the radius is what determines the arc. So our radius is going to be half of our y value, if that makes sense. Because this is our y coming along here. I should probably give you a different color here. Our y is coming along here, which would be the diameter. And the diameter is equal to 2 times the radius. So we could say that the radius is equal to diameter divided by 2. Diameter is our function. So if we're setting this up, we could say that the radius is equal to negative 2x plus 2 divided by 2. That's our 1/2, or negative x plus 1. The formula for a semicircle is going to be pi r squared. However, we only want half of this, so this is going to be 1/2 pi r squared. This is for a semicircle. And finally, we'll go ahead and set up the integral for this. Our volume is going to be equal to the integral going from 0 to 1. There's an element of this that's the 1/2 pi. Now that can either go inside the integral or outside. Many like to put it on the outside because it doesn't really affect the inside, so we'll go ahead and do that as well. And then what we're left with is our radius squared. Our radius is going to be a negative x plus 1 squared and dx. Again, if we think about it, this is where the elements are vertical. They're vertical to the x-axis. Let's take a look at our number 2b over here. In this case, we've been asked to find rectangles of a height 1/4. Now, this is a fixed height, which means that no matter where we're at on this, whatever cross-section we have, it's always going to be a height of 1/4. So if we continue reading, we'll notice that these are perpendicular to the y-axis. All right, that means that we've got a horizontal cross-section going this way. It also means we need to solve for x. So let's go ahead and do that first. We would subtract our 2 minus 2, so this becomes y minus 2 equals negative 2x. Divide both sides by minus 2x, or minus 2. And that leaves us with a x is equal to, I think I'm just going to leave it y minus 2 divided by negative 2. That makes it nice and easy. Okay, so we've got our new x value. This is, again, going with regards to y this time instead of x. And our formula, our cross-sectional area there is going to be 1/4 times our side. Oops. And so when we take the integral of this, it's going to simply be from 0 to 1, I believe. Or 0 to 2, I'm sorry, because we're no longer on the x side. So our integral is going from 0 to 2. And then this is going to be times 1/4. All right, that's our height of that rectangle, times our width, which is going to be our x value here, or y minus 2 divided by 2. And that's with dy. This is with respect to y.